Hi guys, this is Mrs. McDowell. We're going to do section 6.2 notes today, and you can pause this as you go, write down what you need to, and we will review it a little bit on Monday before you do your questions. Remember, we're in this chapter, we're talking about forces in two dimensions. So in more than just a up and down or side to side, we're talking about going in two dimensions. So last section we talked about projectiles, ones that had a vertical and horizontal component. And in this section, we're going to talk about circular motion. So to start that, I want you to watch this little video to talk about circular motion. It gives us a good preview of how things work.
Consider an object moving in a circle at a constant speed, such as a stone being whirled on the end of a string. Is the stone accelerating? Let us examine an object in uniform circular motion. Uniform circular motion is the movement of an object or particle trajectory at a constant speed around a circle with a fixed radius. The position of an object in uniform circular motion relative to the center of the circle is given by the position vector as shown here. As the object moves around the circle, the length of the position vector does not change, but its direction does. To find the object's velocity, you need to find its displacement vector over a time interval. The change in position, or the object's displacement, is calculated by subtracting the two position vectors. You know that a moving object's average velocity is the displacement of an object divided by the time interval in which the displacement occurs. So for an object in circular motion, velocity is equal to the displacement of an object in circular motion divided by the time interval in which the displacement occurs. The velocity vector has the same direction as the displacement, but a different length. You can see here that the velocity is at right angles to the position vector, which is tangent to its circular path. As the velocity vector moves around the circle, its direction changes, but its length remains the same. Let us now find out the direction of the object's acceleration. The figure here shows the velocity vectors at the beginning and end of a time interval. The difference in the two vectors is found by subtracting the vectors, as shown here. The average acceleration is in the same direction as delta v, that is, toward the center of the circle. Repeat this process for several other time intervals when the object is in different locations on the circle. As the object moves around the circle, the direction of the acceleration vector changes, but its length remains the same. Notice that the acceleration vector of an object in uniform circular motion always points in toward the center of the circle. For this reason, the acceleration of such an object is called center-seeking, or centripetal acceleration.
So one of the things that we're going to talk about in this chapter is centripetal acceleration. Now, all of those figuring out the vectors we won't do, but we will understand some of the concepts, and we will look at some of the math that goes along with it. So when we're talking about uniform circular motion, we're talking about the movement of an object, and it's going to move at constant speed around a circle. So it's uniform, but it's in a circle. But is it accelerating? Well, remember when we think back to acceleration, they told us that the position and the speed vectors don't change, but its direction does. So since its direction does, it is accelerating. So anytime we have a change in direction, we have acceleration. These objects that are in uniform centripetal motion have centripetal acceleration. So since they are accelerating, it's called centripetal acceleration because it's keeping it going in a circle. That centripetal means center seeking. It's always pointing towards the center. So the A sub C, the AC, centripetal acceleration, always points towards the center of the circle. Its magnitude, or its size, remember, is equal to the square of the speed divided by the radius of the motion. So this is one equation that we can use to calculate centripetal acceleration. When we want to do that later, we can use this equation here. And when we are looking at the velocity, like they told us in the video, velocity is the radius, or the change in r, the displacement, divided by delta t. And it's going to always be a tangent to the circle. Now that's not too important to us, but just a concept that we will look at. So we can look at the speed of an object moving in a circle by measuring its period, or the t, the time needed for the object to complete one complete revolution. So as we look, we can look at how long it takes to go around in a complete circle from here around. The object then travels the distance equal to the circumference of 2 pi r. So remember, the circumference is 2 pi r. That's the distance that it's going to go around in t. So the speed is v equals 2 pi r divided by the time, or the period, which is t. We can plug that in, substitute it into our acceleration equation that we had before, and we can come up with this equation down here. Again, this is just another one that we can write down to use later on. The acceleration of the object is always in the direction of the net force. So remember, this is Newton's second law, F equals ma. The acceleration is always going to be in the direction of the net force. So since we have centripetal acceleration that's towards the center, the net force must also be towards the center of the circle. And this force can be caused by many different things. Okay, so think about when an Olympic hammer thrower swings the hammer, the tension, the force is the tension on the chain. So she's pulling on the chain, creating a force or tension towards her, and that is going to create the centripetal force. Sometimes friction creates centripetal force when you're turning in a circle. That's going to keep you from going off, sliding off into the other directions. Friction can cause centripetal acceleration, and so can tension, a rope, other things like that. When an object moves in a circle, the net force is, again, like we said, towards the center of the circle, and this is called centripetal force because it is center seeking. And we need to identify the agent that causes that force, like we were talking about, and then we can apply Newton's second law to find that acceleration. So again, Newton's second law doesn't change, F equals ma, except this time we're going to use the centripetal acceleration for our A. The net centripetal force on an object moving in a circle is equal to the mass times centripetal acceleration, like it has been. Again, these are our samples for solving problems. First, we'll find our coordinate system like always. For circular motion, the direction of the acceleration is always towards the center. Okay. The other axis is the direction of the velocity, which is tangent to the circle. We can label that tan. The centripetal force is really the net force in the centripetal direction. It's the sum of all the real forces that we will see on that axis. So here's an example. If we have a 13-gram rubber stopper that is attached to a 0.93 meter string, the stopper is swung in a horizontal circle, and it makes one revolution in 1.18 seconds. So it's going to go all the way around from here around in 1.18 seconds. Find the magnitude of the tension force exerted on the string. So I want to find the force, which is actually my centripetal force. I want to know what that is. Well, I know my mass, and I know my R. This is my radius because it's talking about how it's attached to the string right there. That is 0.93 meters. One thing that we want to be careful of is this is in grams, and when we talk about mass, we need to switch it to kilograms. So 0.013 kilograms. All right, so we are going to use our acceleration. We know our t. This is our period, t. We're going to use our acceleration equation first. Then we can plug it into F equals ma. And we don't know v, so we're going to have to use the 4 pi r, or pi squared r divided by t squared. And if you want to go ahead and check on page 162, you can look at how they work that out on there and check your answer. Go ahead and work that out in your notes. Then I also put the answers to the practice problems on page 162 on Classroom that you can work later when we're done with this. The last thing that we want to talk about is centrifugal force. Why is it that you feel like you're being forced right when the car turns left? When you are playing the lean game, why is it that you end up, if I am turning left, why is it that I feel like I'm being forced right? Is there a force acting on me, or is it just a feeling? Well, Newton's first law tells us that you will continue in motion with the same velocity unless there is a net force acting on you. So the passenger in the car would continue to move straight if there was not a force on the car acting in the direction of the acceleration. So the force is actually pushing us towards the center, making us turn. But I feel like I'm being pressed out because this is basically inertia, something that I am feeling. So this is basically, we call it a centrifugal force or an outward force, but it is actually fictitious. It's non-existent. You feel as if you're being pushed only because you're accelerating relative to your surroundings. There is no real force because there is no agent exerting a force on you. So we can look through these section questions, the section check. See if you know them as you're going through them. All right, so that is the end of section 2. We will go over this a little bit when I get back, but I want you to pause this, write down your answers. I want you to do the practice problems on 162. I have put the answers on Classroom, but I want you to practice them. If you want to go ahead and get a head start on the questions on page 163, you can do that, but we will probably assign them on Monday after we've kind of reviewed a little bit. But if you want a head start, you can go ahead and start on those. Have a great weekend, and I will see you on Monday.